invitation. So I'll describe some work in progress with Raghu Mahajan, who is here, and with Abul Hassan Vezi, where we probe the properties of the SYK model at very low energies near the edge of the spectrum. So let me first remind you about some facts from random matrix theory. So this theory makes predictions for the spectrum of quantum chaotic systems at very small energy differences. And so one classical thing that you can look at is called the nearest neighbor level spacing distribution. It is? Okay, let me switch here. Right. Okay, so the first thing one can look at is the nearest neighbor level spacing distribution. This is where we look at the discrete spectrum of the theory in some, let's say, narrow energy band. We look at the difference between neighboring energy levels, and we plot the distribution of this over, let's say, energies in the narrow band or over different realizations of the random couplings or both. And random matrix theory makes a prediction for the distribution of these differences, which looks roughly like this. In particular, the probability of finding two very nearby energy levels is small. This is level repulsion. So this is one thing that was checked in SYK. The second thing, as Steve described yesterday, is the spectral form factor. So this is where we look at the thermal partition function, and you can think of this as doing an analytic continuation of the inverse temperature to be complex. And this imaginary guy, now you can think of as time. And so you look at the absolute value square of this thing. And if you plot this on a log-log scale, it looks roughly like this. In particular, in this regime here, you get this linear growth in time. This is, again, a prediction of random matrix theory, which is due to correlations between nearby energy levels. All right, so these things were verified in SYK, but we have some reason to believe that if we go to large enough n, if we go to low enough temperatures or energies, then these things will be violated. And this is the subject of this talk. And in particular, the question is there a spin glass phase in SYK? Right? And as I'll describe, there is a calculation you can do which tells you that you should expect a phase transition to a spin glass phase at a very low critical temperature, so which is at or above J times e to the minus square root 2 pi n. So n is the number of fermions, J is the usual SYK coupling, and as I'll explain, you expect something funny to happen below this temperature. So what does this mean? How can we actually go about seeing it? Well, because this is happening at low energies, it's going to have something to do with at low temperature, it's going to have something to do with the spectrum of the theory near the edge. So we have our spectrum. We want to focus on modes which are close to the edge. And over there, on general grounds, we expect that in a spin glass phase, these random matrix predictions are going to be violated. The picture is roughly that once the system becomes a spin glass, everything is frozen. The system is not scrambling anymore. It's not chaotic. And so all these predictions should change. In particular, you should lose the correlations between energy levels. And then this distribution should turn into an exponential distribution. And this is something that you can check numerically. All right. So what I'm going to do is first describe the calculation that gives this temperature, and it's going to come with some caveats. And then I'll describe numerical work trying to find this. So we have some improved numerics where we focus on the low part of the energy spectrum. The bottom line is going to be that we do not see any deviation from random matrix behavior, and this will allow us to put some bounds on this critical temperature. All right. So how do we get this temperature? So the object we're going to be looking at is the SYK partition function with n replicas. So for most of this, I will focus on the usual model with what we call the Q=4 model. This is just the model with 4 fermion interactions with random couplings. And the signature of or one signature of a spin glass phase transition is if you have an operator which is off diagonal in replica space, which condenses. So that signals replica symmetry breaking. And so I'm going to write down the operator that's going to condense. So it's a bilocal and time operator. It has 2 replica indices. So these A, B can go from 1, can be something between 1 and n, but we choose them to be different, so it's off diagonal. And this operator is going to be what we take the G, which is the fermion bilinear, and we square it. So let me write it out in terms of fermion. It's going to be some 4 fermion operator. So this G is the usual fermion bilinear with color indices contracted. And we square it. Right? So I is the color index, A and B are the replica indices, and we look at this thing. Now note that this is actually the minimal amount of fermions you have to put in for the thing to be able to condense. So a single fermion, of course, cannot condense. Fermion bilinear, if you do it, if you put them in 2 different replicas, you can show that also those cannot condense. So 4 is like the minimal number of things you can put in, and this is sort of the simplest thing you can write down. And so let's see if it to see if it condenses, we can compute the effective potential for the 0 mode of this thing, so the static mode of this field. And you can do this calculation, and you find that there is a quadratic piece. There is one term which goes like n, and then there's another term where there's some number here, and it goes like n squared, and then there is a correlator. Right, so there's this correlator you have to compute, basically just twice this f. And then there are higher order terms, which we are not going to care about. And so you see in the effective potential for this guy, there are 2 competing terms. And if this term ever ends up dominating, then the effective potential for this f is going to be unstable. It's going to condense, and that's where the phase transition is going to happen. So far, everything I'm saying is exact, but now we have to compute this correlator, and for this, we have to do some approximation. All right. So the simplest approximation we can take in this correlator is we can take the large N strong coupling limit, and we can contract the fermions that show up here in a single replica and contract them using the conformal propagator. And so once you do this, you find the following answer. So because we're doing contractions here with fermions in different replicas, there's going to be an n suppression. There's also going to be a log divergence coming from these integrals. And this ends up being the correlator, the effective potential in this approximation. And so when you ask when does the sign of this flip, it happens at this temperature, right? And that's the phase transition. Now, about this answer, I have good news and bad news. So let's start with the bad news. The bad news is that if you actually try to see this numerically, it's very, very hard. So let's say that we want to do this, as we said, by checking the level spacing distribution. And let's say we only look at just the 2 lowest levels in the spectrum. So to have the 2 lowest levels accessible at this temperature, we need this temperature to be greater than the gap between the 2 lowest levels, which goes like e to the minus n in this system. Now, you see at parametrically large n, this will become accessible, but it turns out that they actually see this once you plug in all the numbers, and should be above at least 80. We need at least 80 fermions, which is way beyond what we can do numerically. So that's the bad news. The good news is that we probably shouldn't take this answer at face value. And the reason is that we made an approximation here to compute this correlator. And this approximation is valid in the limit where we take large n first, and then we take the strong coupling limit. That's how we got this answer. But here we are extrapolating this to a limit where the coupling is much, much bigger than n. The coupling is of order e to the squared of n. It's very large. So this is outside the regime of validity of our approximation. So there are going to be large corrections, perhaps, that can overwhelm this log. But the good thing is that you can actually show that this correlator, you can actually write this as a sum of squares. So you can actually check that this sign here is never going to change, right? And so even if there is something, let's say you find here that there is some log plus some beta j over n to some power, let's say, which overwhelms this log, it's still going to come with an overall minus in front. And so all this thing is going to do is just push the critical temperature up, right? And so barring some miracle that's going to kill the log, at least on general grounds, we do expect the transition to be there and the temperature to be bounded below by that. All right, so that's the analytic evidence that we have for this spin glass phase transition. Well, yeah, so the way you get this is, so the easiest way to get this is to start with, so you have an action which is roughly psi to the 2q, which you get after doing the disorder average. And then you just introduce this auxiliary field. So you have like f square minus f psi to the q. Right? This psi to the q is going to be this g to the g square thing. And it's basically this minus that's going to be there. That's all there is. So you sort of expand this to second order, and it's this minus that's gonna play the role. Right. Yes. One more thing I want to mention is what happens at different q. So I talked about q equal 4. You can also do this for different q's. So for or the thing you can actually do is to take this f operator to be g to the q over 2 in general q. That turns out to be the thing that gives the same log divergence. So when you do this, what you find is that for q equal 2, 6, 10, and so on, there is no phase transition. And for q equal, for q equal 4, 8, 10, there is a phase transition, but the power of n up here changes. So for example, for q equals to 8, what you find is that the critical temperature is like e to the minus n to the 3/2. This is parametrically smaller than the gap. And so this is something we're never going to see, at least not by looking at the level statistics or looking at the spectrum. So I would say that this q equal 8 phase transition, if this is actually the answer for the critical temperature, it's inaccessible. And the power just gets, sorry, this is 12. The power just gets bigger and bigger as we turn up q. So this leaves, again, up to these corrections, it leaves q equals to 4 as the interesting theory for this phenomenon. All right. So that was the analytic evidence for the spin glass transition. And I'll describe the numerics we used to try and see it. So again, the idea is that we're going to focus on the low part of the energy spectrum. We just want to compute a few states at the edge and see how their difference is distributed. And for this, for focusing on this part, we used two basic techniques for focusing on this part and for going to a larger n than we had before. So one technique is we used what's called the Langshos algorithm. This algorithm, given a matrix, lets you compute just the low part or high part of the spectrum. The basic idea is that, let's say you just want to compute the extremal eigenvalue of a matrix, then you would take your vector, you would act on it with your matrix, the Hamiltonian, you would do this repeatedly, eventually it's going to converge to the extremal eigenvector, and then you can compute the eigenvalue. And Langshos is sort of a sophisticated version of this basic power method that just converges faster. So this is what we implemented. The useful thing about Langshos, just like this method, is that it doesn't need access to the full Hamiltonian matrix. All it needs is this function where you give it a vector and it acts on it with a Hamiltonian. And this allows for many optimizations that sort of speed things up because you don't have to store the whole Hamiltonian in memory. And the second thing we did was, instead of using ordinary processors, we implemented this on GPUs. So GPUs were originally invented for accelerating graphical calculations, but nowadays you can use them for doing general programming. And the basic idea is that each GPU has many cores, like let's say tens of thousands of cores. Each one of these cores is slower than the CPU you have in your laptop, but they're all running in parallel. So if you can actually make use of all this computational power, then a single GPU is going to replace, it's a bit hard to compare, but let's say around 10 to 20 of the CPUs that you have. And so even with a relatively modest number of GPUs, you can actually get a very large amount of computational power. And so running on these GPUs and using this algorithm, we did numerics with up to 46 fermions and with about 500 samples of 200 eigenvalues each. This is up from, like before, with full diagonalization, we had 34 fermions. So this is quite an improvement. And then we checked the level statistics. I shouldn't write here. Majorana, yeah, these are the Majorana fermions. Right. Now, when checking the level statistics, it can get a bit tricky because you have to control for the mean density, mean energy density in order to actually make this comparison with random matrix theory. And at the edge of the spectrum, this has large fluctuations. It turns out that the simplest way to do this is to really just literally look at the two lowest lying states in the spectrum and look at the distribution of their energy. And this already gives a comparison to random matrix theory. And if we're just looking at the two lowest energy levels, that means we're actually looking at the lowest possible temperature that we can. And so the temperatures that we have here are basically the same as the gap. And for those numbers, this is about 1/2000. And so if you can compare this with n, this means that because we're not seeing a phase transition, this means we can rule out critical temperature, which is down to order about 1/n². Okay, so this is sort of how far down we can go with these numerics, assuming these corrections change the critical temperature to be of some power of the n, like you would expect. All right, and this is what we can rule out. On the other hand, we have this lower bound on the critical temperature from the analytics, and so we expect the spin glass phase to be somewhere in this regime. And again, I should emphasize the numerics are not in contradiction with that analytic result because that's just not accessible numerically. Let's see how much time I have. All right. So in the few minutes I have left, I'll describe another result that we got from this data. So another thing you can look at is the ground state distribution. This is where you just compute the ground state energy of many different realizations, and you ask, how is this distributed? So in random matrix theory, there is a prediction for this. It's a Tracy-Widom distribution. In SYK, it turns out that it's simpler. The ground state distribution to a good approximation seems to just be a Gaussian. And you can check this by looking at some higher moments of the distribution. So again, thanks to this Langström algorithm, because we're just interested in the ground state, we can very quickly collect a lot of statistics, so we can make precise predictions about this. All right, so we think it's a Gaussian. The mean of this distribution of the ground state energy we can extrapolate it to large N, and we get the E0 parameter that was computed analytically, thermodynamically. This was this minus 0.04 N. This is the number that you get from a large N calculation, and so this converges. You can also look at the variance, and it goes down like 1 over N to some funny number, 3.4, which we don't have an analytic understanding of. But then we can take this fact and say something about the behavior of the thermal partition function at large beta. So if we think about log, what we call the annealed free energy, log of Z, then from these two things, we know that it must include the following two terms. So there's this ground state contribution, and then there's this contribution coming from the variance, and there are no higher order terms, just because this distribution is Gaussian. So we know that these terms have to show up, and at large beta, there are no higher order. So when I say higher order, I mean there are no higher order terms in beta, things that would diverge faster at large beta. And one final funny fact about this is that when you go to such extremely low temperatures, it turns out that this annealed free energy is different than what we call the quenched free energy. So in this model, typically at higher temperatures, these things agree, but at these extremely low temperatures, they don't agree anymore. Here, when you just plug in a Gaussian distribution, you just get this ground state term. And you don't see this divergence. So this would, analytically, this perhaps comes from a breakdown in, again, replica symmetry. That's it.